Right now, I want to address something I mentioned in the end of part 2 of previous video about an unbounded integrand. If you looked at this particular integral, the integral from -3 to -1 dx over cubic x plus 2, it turns out if you do it carefully, you do get 0, which is what the picture suggests. And the picture, though, suggests you might be able to do that very quickly with a symmetry argument. That this function, it gives exactly certain positive values over here and corresponding negative values here. This area should be the positive, and this should be exactly its negative, and they should cancel out. That's a very, very dangerous thing to do, and I want to show you an example where that doesn't work. Here it happens to give you the right answer, so you might start to be convinced, well, I'm going to do that a lot. So it's very dangerous to use symmetry because you get in danger of saying infinity minus infinity equals 0, and that is the worst sin with infinities. So let me do a more basic case. And we're going to go back to an improper integral of type 1, where the issue is that the interval is unbounded. And I'm just going to look at a very simple function, y equals x, or f of x equals x. We know what the graph looks like of that. It's just a straight line. And we'd like to know, does this integral make sense? Can we say that that's just equal to 0? You could say, okay, here's this region over here. It's exactly corresponding here. This is an odd function. And I've got a symmetric interval, certainly, the whole real line. So maybe this plus cancels out this minus. This is definitely a case, if you think about it, where we are really trying to say infinity, which would be this right-hand side on its own, minus infinity, that would be the contribution here to the integral, equals 0. And why can't you do that? Why is that so dangerous? So here's one reason why it's so dangerous. I'm going to use that to prove that, in fact, infinity equals 0, which is an interesting thing to prove. Okay, so I don't want that yet. So here's what I'm going to do. I'm just going to do some manipulations with integrals. And the one manipulation I'm going to do is something we do all the time with integrals. And if it's illegal, then our whole thing about integrals comes crashing down. So I'm just going to say, you know what? The function x is the same as the function x minus 1 plus 1. Okay, so okay, let me just go ahead and start. I'm saying, yeah, this is going from here. Okay. So if this makes sense as a number, for example, maybe you're asserting it's equal to 0. Okay. Then it should be equal to this guy. And then I should be able to split that up. One of our fundamental principles of integrals is that they're linear, that the integral of a sum is the sum of the integrals. So we're going to get this guy. Oh, I still want parentheses there. I'm going to get this thing, and then plus the integral of something rather simpler, just 1. I think I want a space there. Okay. Very simple. Okay, now, if we believe this argument that by symmetry around the origin, this should have been 0. Okay, so now I'm going to put in an explicit value there. It's looking weird here. Okay. Then, well, let's look at this function. Y equals x minus 1. What does the graph of that look like? You could probably picture it in your head, but here it is. It's a straight line. You know what? It's exactly symmetric about the point 1, 0. That exact same argument should work to say that this triangle counterbalances, cancels out with this triangle. It looks asymmetrical here just because I have an interval that was a finite interval that was symmetric around the origin, but if I just move that, it's going to look more similar. And of course, the point is the interval is the entire real line, so that's still symmetrical around that point. Okay, so if we believe that argument that symmetry says that's 0, that's 0. But integral from minus infinity to infinity of 1 dx, that's the area under y equals 1 from minus infinity to infinity. There's no possible answer for that but infinity. Okay, so now I've derived that infinity equals 0. This is totally bogus. And this is exactly the kind of trouble you get into when you start dealing with infinite quantities and trying to say, oh, they cancel out. So again, from the very first, the first place we should have been suspicious is I'm saying this positive contribution on the right and this contribution cancel without actually verifying that they're honest to God finite numbers. The reason it actually made sense here, the reason the answer was 0, it was defined, the integral converges and it's 0, is that the integral from -2 to -1 is a finite number purely on its own. The integral from -3 to -2 is a finite number purely on its own. They happen to be exactly equal and opposite, and so when you add, they did get 0. But you can't just blithely, without verifying that the individual pieces converge, you can't just say the answer is going to be 0 by symmetry. You get into nonsense and false proofs that like 0 equals infinity, things like that. You can use slightly different examples to prove that 0 equals 1, things like that, but just using exactly the same kind of reasoning. So if you're wondering, why does the book say you have to split this up and do the parts separately and verify each part separately? It's because you can get into absolute contradictions and nonsense if you do not.